Hello friends, welcome to my channel. In this video, we will learn about gate questions which are based on NMOS transistors. With the help of the formulas explained in the previous lecture, you can solve the questions that are frequently asked in gate examination. So let's get started. The first question is, for the transistor M1 as shown in the figure, mu n Cox is given, W by L is also given equal to 10, where mu n is the mobility and Cox is the oxide capacitance per unit area, W is the width and L is the length. The channel length modulation coefficient, that is lambda, is ignored if the gate to source voltage is 1 to keep the transistor at the edge of saturation. Then they are asking you to find out the threshold voltage. So to do this question, we need to first understand that it is given that this transistor needs to be at the edge of saturation. For this transistor, which is an NMOS, to be at the edge of saturation, the condition that needs to be satisfied is VDS should be equal to VGS minus VTH. Now in this figure, the VDS is, this is the drain terminal, this is the source and this is the gate, because this is a NMOS transistor. So we know that VDS can be written as Vout minus 0, which is the source potential. VGS can be written as the input voltage, and VTH is what we need to find. But it is given to us that in order to keep the transistor in the edge of saturation, VGS value is 1 volt. So we know that to keep it in the saturation mode, this is the condition that needs to be satisfied, that Vout should be equal to 1 minus VTH. So now we will try to use this equation and find the value of VTH. Also, in the figure, you can see that the value of Vout, if calculated, will be VDD minus the drain current into the resistance, that is RD. The value of VDD given is 3 volt and RD is given to be 20 kilo ohms. The value of drain current is what we don't know, but we know the formula, and because we are considering the edge of saturation mode, so we are taking it that the transistor is in saturation. Hence, the ID or the drain current equation will be half mu n Cox W by L VGS minus VTH and whole square. You are given all the parameters except the value of VTH, which we need to find out. So we will put in the values that are given in the question. We are given mu n Cox value, we are given W by L, and we are also given the value of VGS is equal to 1 volt. So we'll substitute those values and we have ID is equal to half. Mu n Cox is given to be 100 microampere per volt square. So this is 100 into 10 to the power minus 6. W by L is given to us as 10. So this is 10. VGS is 1 and VTH is the unknown. So this is what we get. Now if we just solve it, this is 10 to the power minus 3 divided by 2, 1 minus VTH whole square. This is the drain current. Now we will substitute this drain current, that is equation 2, in equation 1. And we also have the main equation that Vout is equal to 1 minus VTH. So we'll try doing this. First of all, we'll say Vout, which is equal to 1 minus VTH, is also equal to VDD, which is given to you in the question as 3 volt. So VDD is 3 volt minus ID that you have just found with the help of equation number 2 and multiplied with 20 kilo ohms, which is the value of the resistance. Now after doing this substitution, we get 1 minus VTH is equal to 3 minus this 10 by 3 and this gets cancelled. 2, this becomes 10. So we have 10 into 1 minus VTH whole square. And now it's just solving a mathematical equation to get the value of VTH. So if we solve it, we'll get over here 1 minus VTH is 3 minus 10. We'll just open this. 1 plus VTH whole square minus twice of VTH. This becomes 1 minus VTH is 3 minus 10 VTH square plus 20 VTH. Now we'll just try to bring the like terms at one side. Now friends, when you will solve this equation, you will get the value of VTH as it would be, this equation can be solved like 5 VTH, splitting the middle terms, and you will get this type of expression. Minus 1 is 0. Now when we try to find out the possible values of VTH from here, we get either VTH could be 8 divided by 5 or VTH could be 1 divided by 2. Now 8 divided by 5 will come out somewhere around 1.6 volt. Now if you take VTH as 1.6 volt, then your VGS value is at 1 volt. So what will happen in that case? The problem will be that VGS will become less than VTH. If I take that the VTH value is 1.6, that is 8.8 by 5. So in this case, 1 volt would be less and the transistor would actually go in the cutoff mode. So this 1.6 is not possible. Hence, we need to consider the next possible value of VTH, which is equal to 0.5 volt. So the answer to this question is 0.5 volt. Let's move to the next question. In the circuit shown below, the W by L value for M2 is twice that for M1. The two NMOS transistors are otherwise identical. Threshold voltage is 1 volt. And there is a condition given that the VGS for the M2 transistor must be greater than 1 volt. They have also given you the current equations for both the linear and the saturation mode. And now they are asking you the voltage at Vx up to 2 decimal places. So let's get started with this question. How do you do this? First of all, you should find out that what is the mode of operation of each of the transistors. And based on that mode of operation, you may come up to using either this equation, which is for the linear mode, and this equation, which is actually for the saturation mode. Let's first work out for the transistor M2. Now for M2, this is the drain, this is the source and the gate terminal, depending on the voltages and the diagram given to you. Depending on this, we can find out the value of VDS for this second transistor. This is 3.3 minus of Vx, and VGS is equal to 2 minus Vx. Now, if you consider the effective voltage, then you need to subtract the threshold also from here, which is given to you as 1 volt. So actually we are trying to compare 3.3 minus Vx and 2 minus Vx minus 1, which is 1 minus Vx. Now if we ask you to put an equality sign that which among these two is greater, either this is greater or this, you can easily understand that because Vx is common in both of them, so definitely 3.3 is greater than 1. Hence, this transistor satisfies this equation that VDS is greater than VGS minus VTH, hence it is in saturation. Now coming up to the next transistor, that is M1. Talking about M1, this is the drain, source and the gate. Now if we do the same analysis, the VDS1 for this M1 transistor is actually Vx and the VGS1 is equal to 2 volt. Now here you subtract the threshold voltage, that is 1, so you will get 2 minus 1, which is 1 volt. So we are now comparing this 1 volt with Vx. But we actually don't know what is the value of Vx, so we are a little confused that how do we decide whether this transistor is in saturation or linear. Because if Vx is greater than 1, then it is in saturation. If it is less, then it is in linear. To decide this, you need to look upon to the condition given that VGS for M2 should be greater than 1 volt. Now, keeping this in consideration, let me just write down what is actually VGS for the second transistor. Looking at the diagram, you can clearly understand this is 2 minus Vx. This should be greater than 1, which actually means that 1 should be greater than Vx. So yes, you get a analysis for the value of Vx. This is what the value of Vx is. So Vx will never go beyond 1. It is always less than 1. So when you know that this Vx is always less than 1, hence you can interpret that the first transistor is in linear. So we come up to a decision that this is in linear mode and the M2 is in saturation. Now we are in the position to use the drain current equations given to us, and we will simply equate the drain currents and find out the value of Vx. So let's get started. So first of all, I'll write ID2. This is using this formula. So mu Cox W by L of 2 should be, now VGS value is equal to 2 minus of Vx minus 1 whole square, and this is all divided by half. So this becomes equal to ID1, and for ID1 you will use this condition because that is in the linear mode. So mu n Cox W by L1, and we'll write VGS for this is 2 minus 1 into VDS, which is Vx, minus Vx square by 2. Yes, so this is what you get the equations, and you are also given one more information that you should not forget. W by L for M2 is twice of M1. So yes, we need to consider this. Rest all the parameters are same. So if that is the case, I can simply cut these mu n Cox from here. Actually, this is also mu n Cox. So I'll just cut this out. But I know that this W by L is actually twice of W by L1. So this 2 will get cut when I try to equate them. And I am left with 1 minus Vx whole square is equal to Vx minus Vx square by 2. So you get 1 plus Vx square minus twice of Vx is equal to Vx minus Vx square by 2. Let's try to solve it for the value of Vx. Friends, when you will solve this equation and try to find out the values, you will get either Vx is 1.5773 volt or Vx is equal to 0.4226 volt. Now you already know that this is not possible. Why? Because we are clearly given that Vx has to be less than 1. So hence we can quickly make up the decision that this is the correct answer and this is what the value of Vx should be. So the answer to this question is 0.4226, and they are asking us up to 2 decimal places, the 0.42 volt. So this is the way how you will solve this question. Let's move to the next question. Again, we have a question from 2017. For the circuit shown, assume that the NMOS is in saturation. Now, in this case, we are given that this transistor is in saturation. So that's a good thing. And the threshold voltage is also given as 1 volt. The transconductance parameter mu n Cox W by L is also given 1 milliampere per volt square. We need to neglect the channel length modulation, that is lambda, and the body biasing effect, so you need to ignore that, and simply we need to find the drain current in milliamperes. First of all, we know that this transistor is in saturation, hence you know the equation for the drain current is half mu n Cox W by L VGS minus VTH whole square. In this transistor, the value of VGS, first let's try to find out that. Now you can see this is the gate terminal, this is the source, and this is the drain. Now the gate terminal is at a voltage which would be at this particular point. To find out the voltage at this point, you can apply the simple potential divider rule, because we are given VDD is 8 and we are given these two resistances, 3 mega ohms and 5. So if I try to apply the potential divider rule, then I'll get this VG is 8 into 5 mega ohms divided by 5 plus 3 mega ohms. So this becomes actually 5 volt. So we come to know that this point is at 5 volt. Hence, the VGS is 5 minus. Now, this potential Vs is actually, you know that the drain current is flowing through this. So this same ID is flowing. And we need to find ID in milliampere. So let us assume this value ID is in milliampere. And if you want to find out the potential at this source, you will multiply this drain with the resistance that is 1 kilo ohms given to you, this RS. And because I am assuming that ID is also in milliamperes and this is a kilo ohms, so that milli and kilo will get cancelled. And I can simply say that this VGS is equal to 5 minus ID. Now keeping this in mind, I can move to solving the equation. This is your first and that's your second to find and get to the answer. Let us substitute the values that are given to us. We are actually given the value of this mu n C ox W by L is 1 milliamperes, and we are still considering that the drain current will be in milliamperes. So I am ignoring that milli and I am just keeping the 1 that is given to me. So I did not use this milliampere right now. And Vt value is also given as 1 volt. VGS, we don't know what it is, but we know that VGS is equal to 5 minus ID. So minus of 1 volt. And now I can substitute over here ID is equal to half. And instead of VGS, we can write 5 minus ID minus 1 whole square. We can say ID is equal to half 4 minus ID whole square. So now we can try to solve this. Let's pick up ID constant. So common ID minus 8 minus 2, ID minus 8 is equal to 0. So ID is equal to either 8 milliamperes or ID is 2 milliamperes. Now I need to decide which value. If I take ID as 8 milliamperes, then this equation will give me VGS as a negative value, and that is not possible, because if VGS is negative, then this transistor will move in the cutoff mode. So hence ID cannot take up the value greater than 5. So definitely the value of ID which is correct is 2 milliamperes. So the answer to this question is 2 milliamperes. Let's move ahead to the next question. Two N-channel MOSFETs T1 and T2 are identical in all respect except that the width of T2 is W is twice that of T1. So we'll just note down what data we are getting. Both the transistors are biased in the saturation mode, so you know that they are in the saturation mode. But the gate overdrive voltage of T2, that is VGS minus VTH of 2, is again double for that of 1. Where VGS and VTH we know are the gate to source and the threshold voltage. If the drain current and the transconductance, so drain current is ID1 and GM1 for the first transistor. So they are asking you to find out the values of ID2 and GM2. Now friends, first of all, we know that because this transistor is in the saturation mode, so we can quickly do it, that ID2 equation will be equal to half mu n Cox W by L of 2 VGS minus VTH whole square. Now you are given in the question that for the second transistor the width is double, so I will get a twice in the numerator. Rest all the parameters are same, so these parameters are same. Only the thing is that this width becomes twice and over here the effective voltage is also twice as compared to the first transistor. So because of a square we will have a 4 in this case. So total you will have ID2 8 times of ID1. So that is the first thing. Now next is GM. GM is actually defined as the transconductance del ID by del VGS, and the formula for this is mu n Cox W by L VGS minus VTH for the transistor to be in the saturation mode. So this you can easily derive by just differentiating this equation with respect to VGS. Now when we do this, now you just need to take care that you are trying to find out these things for the second transistor. Again, I know that the width is twice that of the first one and the effective voltage is also twice. So I'll have 2 into 2, that is 4 times. So GM2 would be 4 times that of GM1. Hence, we can have the correct option as the B option, 8 times the drain current and 4 times the transconductance. Yes. So let's move to the next question. Assuming that the transistors M1 and M2 are identical and they have a threshold of 1 volt, the state of the transistors M1 and M2. Now in this question they are not asking you to calculate any values, but they just want to know the mode of operation, that which mode are the transistors in, whether they are in saturation, linear, or one is in saturation, the other is in linear. So let's try to work it out. First of all, let's understand for this transistor that what is the mode of operation. So this is the drain, source, and the gate, because this is an NMOS. So if I write VDS, this is 3 minus, let me assume that this voltage is some voltage Vx. So 3 minus Vx. The VGS for this transistor is 2.5 minus Vx. Now the work is you just need to compare this VDS with VGS minus VTH, and VTH is given to you as 1 volt. So let me write the value. 3 minus Vx needs to be compared with 2.5 minus Vx minus 1. So this is actually 1.5 minus Vx. Now you can easily understand that this value will be greater because Vx can be cancelled and 3 is obviously greater than 1.5. So definitely the M2 transistor is in saturation. So we know that they are asking for M1 and M2. Either this is correct or this is correct. These two options are straight away wrong. So you can work it out and now you have 50-50 chances that what is the correct answer. So to find the correct answer, we need to interpret the mode of operation for M1. Let us write down the same things for M1. This is the drain, source, and that's the gate terminal. If you write the VDS voltage, that would be equal to Vx, and if you write VGS, that will be twice 2 volt, and minus VTH would be 2 minus 1, that is 1 volt. If I try to find out what is VGS for the second transistor, it is equivalent to 2.5 minus of Vx, and this value should be greater than the threshold, which is 1 volt. So we know that Vx should be less than 1.5 volt. So this is what we know. But depending on this, again we cannot find out that whether this transistor would be in saturation or in linear, because even though Vx is less than 1.5 volt, this transistor M1 could be in saturation, could be in linear. So let us assume that, let's say it is in the saturation mode first. If the transistor M1 is in saturation, then we need to substitute and equate both the drain currents equivalent to each other. For the second transistor, we know definitely it is in the saturation mode. So we'll write down half mu n Cox W by L, and VGS minus VTH is 2.5 minus Vx minus 1 whole square. So this is the case, and if ID1, if this is also in saturation, then half mu n Cox W by L, and over here we'll have VGS minus VTH, that is 2 minus 1 whole square. Now you can quickly say that all these things can get cancelled because the parameters are same and it is given that both the transistors are identical. So hence we are left out with 1 is equal to 1.5 minus Vx whole square. We will try to solve this out. We can say that plus minus 1 is equal to 1.5 minus Vx. If we take the under root, let me consider both the values. If I say this is plus 1, then Vx would be equal to 1.5 minus 1, that is 0.5. And if I consider minus 1, then Vx would be equal to 1.5 plus 1, which is equal to 2.5 volt. But you know that this Vx value has to be less than 1.5. So hence we know that the Vx value should be equal to 0.5. If Vx is equal to 0.5 volt, coming back to this analysis, Vx, if it is 0.5 volt, then 0.5 volt is obviously less than VGS minus VTH, which is 1 volt. This means that the transistor M1 cannot be in saturation. It is in linear actually, but you have assumed that it is in saturation. So let us now assume the next way, that if it is in linear, if M1 is in linear, because we understand that it cannot be in saturation. For saturation, the possible value of Vx coming out is 0.5, but 0.5 does not satisfy this condition. Hence, this assumption is actually wrong. So we have already got to know the answer, but just let's prove ourselves. So now in this case, the right side will remain the same, half mu n Cox W by L and 1.5 minus Vx whole square. But this side we will have mu n Cox W by L, and we'll write VGS, which is equal to 2 minus 1 into Vx minus Vx square by 2. So I have written the drain current equation for the linear mode. Now you can cancel out this with this, and we will be left with Vx minus Vx square by 2 should be equal to half of 1.5 minus Vx whole square. If you try to solve this out, you will get two values of Vx. One would be 1.911 and the other would be Vx equal to 0.588 volt, obviously. Again, in this case, this value is not possible because we have already stated that Vx should be less than 1.5. So you are only left out with the possibility that Vx is equal to 0.588. So actually this thing was not required to be done if you just want to answer this particular question. But in case if they ask you what is the value of Vx also in exact way, just like in the previous questions we have done, then the answer would have been 0.588. So in one question only you can understand both things. Hence the correct answer in this case is C. M1 is in linear and M2 is in saturation. Let's move to the next question. Consider an N-channel metal oxide semiconductor field effect mod transistor with a gate to source voltage of 1.8 volt. Assume that W by L is 4, mu n Cox is 70 into 10 power minus 6, the threshold voltage is 0.3 and the channel length parameter, which is actually lambda, is 0.09. In the saturation region, the drain conductance. So friends, they are asking you the drain conductance. Drain conductance would actually mean del ID upon del VDS. So this will be equal to 1 upon the drain resistance RD, because they are asking you the conductance. So you need to differentiate the drain current with respect to VDS, and this would be actually equal to 1 upon RD, and this 1 upon RD is equal to lambda times of ID. So these are all the formulas that we need to know, and knowing this, okay, if you don't know this formula, then also you can come to the derivation. ID for the saturation mode is half mu n Cox W by L, and we have VGS minus VTH whole square. But considering the channel length modulation, we have an extra parameter 1 plus lambda VDS in the drain current equation. Now let us just derivative of this equation. Let us just do the derivative of this equation with respect to VDS. You would get half mu n Cox W by L, and this would be VGS minus VTH whole square dot with lambda. So this would be the derivative, and that's what is asked to us in the question. And if you just look at it, this part of your equation is actually the drain current when you don't consider the channel length modulation. So this is what I was saying, that they are asking you lambda times of ID. So now we just need to substitute the values. Mu n Cox is given to us as 70 into 10 to the power minus 6. W by L is given as 4. VGS is given as 1.8. The threshold voltage is 0.3 and lambda is 0.09. So all the values are given. When you will calculate it, that is 28.35 microsiemens. So that would be the answer, 28.35. So this is how we do this question. Let's move to the next question. Now consider a long channel NMOS transistor with the source and the body connected together. Assume that the electron mobility is independent of the VGS and VTH. So what is given to us is that there is an NMOS transistor and the source and the body are connected. So this is the drain, gate, source, and that's the body terminal. And we are also said that GM is equal to 0.5 microampere per volt for VDS 50 millivolt and VGS 2. And we are also given GD is this for VGS 2 and VDS 0. GM and GD are actually the drain current derivatives with respect to VGS and with respect to VDS respectively. So what you are asked is the threshold voltage of the transistor. Interesting question. Let's first work out for GM. For the GM, you are given 0.5 microampere per volt, and in this case VDS value is 50 millivolt and VGS is 2 volt. First of all, you need to decide that which mode the transistor is in, if this is the condition. Now you very well know the threshold voltage is not given to us, so we have actually VDS which is 50 millivolt, very less, and VGS is 2. So even if I don't know what is the threshold voltage, I know the threshold voltage would be less than 2 volt because this transistor is at least on as I'm given this data. So that is why this side is definitely very less as compared to VGS minus VTH, which is the effective voltage. So you know that the transistor is definitely in the linear mode. If considering that it is a linear mode, it is mu n Cox W by L VGS minus VTH, and you have VDS minus half VDS whole square. Now because they are talking about GM, which is delta ID upon del VGS, this is what is GM and it is given in the question also. So we'll try to differentiate this with respect to VGS. So what we get is mu n Cox W by L, and you will get this thing, mu n Cox W by L dot with VDS when you do the derivative. All the other things will be 0. So now we'll just substitute. We are given the value of Gm is 0.5 into 10 to the power of minus 6. Mu n Cox is not given to us, so let us assume this is some constant Kn, mu n Cox W by L. VDS is given to us, which is 50 into 10 to the power minus 3. From here you can find out the value of Kn. So Kn would be 0.5 into 10 power minus 6 divided by 50 into 10 power minus 3. This will come to be equivalent to 10 to the power of minus 5. Now, knowing this Kn value, let's work out for the second condition now. For the second case, it's given GD is 8 microamperes per volt and VGS is 2 and VDS is 0. So I'll just quickly write down. GDS is 8 microampere per volt and VGS is again 2 volt but VDS is 0. So VGS is 2 and VDS is 0. Again, if you notice, comparing VDS and VGS minus VTH, the VDS value is very less as compared to VGS minus VTH. Hence, the transistor is in the linear mode. Again, the drain current equation would be the same as written above. Mu n Cox W by L, VGS minus VTH dot with VDS minus half VDS whole square. Now friends, this time because you're working for GDS, you need to differentiate it with respect to VDS as given in the question. Hence, we will just differentiate this equation. This is our constant, that is Kn, and this side you would get when you differentiate with respect to VDS, VGS minus VTH minus of Kn divided by 2 into 2 of VDS. So this is when I do the differentiation. Now the values given to us is JDS is equal to 8 into 10 to the power of minus 6. Kn we just calculated. So let's keep it right now Kn only. VGS is given as 2. VTH is what we need to find. And VDS is given as 0. So hence we are left with 8 into 10 to the power minus 6 divided by Kn. Kn is 10 to the power of minus 5 is equal to 2 minus VTH. When you solve it, is equal to 2 minus VTH, you will get 8 by 10 is equal to 2 minus VTH. Upon solving, you will get VTH value is equal to 1.2 volt. So hence, the answer to this question is the threshold voltage is 1.2 volt. Coming up to the last question, a MOSFET in the saturation mode has a drain current ID of 1 milliampere. This is a simple question and VDS is 0.5. The channel length modulation parameter is 0.05 volt. The output resistance, so they are just asking you the resistance, that is RD. So we just talked about this, that RD is actually 1 upon lambda times of ID. So that is what you just need to do, 1 upon 10 to the power of minus 3 into 0.05. So when you just do it, this is 1000 divided by 5 into 100. So you will come up to 20 kilo ohms. The answer is 20 kilo ohms. So that is what they are asking you in kilo ohms. So in this way, we can solve the questions based on NMOS. In the next part, I'll bring to you much more questions based on the same topics. If you like the video, then hit the like button below, share it with your friends, and be sure to subscribe. I will see you in the next video. Thank you for watching.